Hello, everyone. My name is Kenya. I work at Vision Research as the communication specialist here. I'll be administrating the webinar today. If you have any questions at all, please feel free to either post them in the open chat or message me directly. The presentation should run about 20 to 25 minutes with 5 to 10 minutes of questions at the end. We will be available after the webinar for one-on-one discussion if you have any more in-depth questions. And without further ado, we're just going to go ahead and get this started. I'd like to introduce you to Kyle Gilroy. He is our senior field applications expert here at Vision Research. And Kyle, you can take it away.
Thanks, Kenya. Can you hear me okay?
I can. You sound great.
Perfect. Hello, everybody. Thank you, Kenya, for the introduction. So today we're going to be giving a very short webinar on high-speed Schlieren imaging. So the first thing that I would like to ask is, why is everybody here today? And for the most part, I think most people would answer would be to learn how to make invisible flows visible. All right. So what are some examples of some invisible flows that we see every day? All right. So you can think of coughing or respiration, airflow during flight, shock waves from a supersonic event, water flow motion, acoustic waves, and heat from some type of industrial process like welding, for example. All right, so let's do a thought experiment. Why don't we see these things? All right, why don't we see these transparent events? What is happening to the light during these transparent flows? All right, so the one experiment I always like to talk about is with a candle. All right, so if that's our eye on the right-hand side, and that's a candle on the left, and that candle naturally has heat that plumes off of it. There's a flow of heat and byproduct coming off of that candle plume. If we go ahead and shine light on that candle, all right, white light is comprised of photons of different wavelengths, right? What happens to those photons when they go through that candle and by that candle? All right, the photons hitting the candlestick will get scattered, and you'll see that they come back to our eye to create an image. All right, the flame from the candle is emitting photons that will also make it to our eye. However, the photons that go through the heat wave will get refracted, but will not make it back to our eye. Thus, we cannot see this flow. Okay, so the question is really, how do we get these refracted photons to our eyes so we can visualize them? Okay, and before we go to that step, we have to ask ourselves, what is refraction? All right, refraction can be defined by something called the refractive index, and that determines how much the path of light is bent. Okay, and we observe this commonly, basically every day. All right, so if you live in an area where the road gets very hot, all right, you'll see that as you're driving down the road, you'll see a little, sometimes it looks like a mirage or maybe some water on the road. This is indeed due to the heat caused by the pavement on the air above it, which will change the refractive index of the air relative to the air around it, and there it will bend light in a different way. Okay, same thing if you put a pencil in water. All right, the reason why the image gets distorted like that is because the photons that bounce off that pencil when they're in water will refract differently than those that bounce off of the pencil outside of the water in air. All right, we also take advantage of this effect of refractive index, the ability to bend light, through the use of lenses. All right, the reason why we have basically curved lenses is because they essentially resize images to project images onto sensors. All right, so these are some examples of what refraction is. So physically, what affects refractive index? All right, if you look at the formal definition of it, you'll see that refractive index is typically defined by the letter N, okay? And it's affected by temperature, pressure, and also the composition of the medium. Okay, so if you take into account all these different variables, you'll see that we can manipulate this refractive index to visualize it. Okay, and here's a candle where you can visualize the refractive index gradient around the heat plume. All right, so how do we do this? So the methods to visualize refraction, the optical methods, and that's what we're here to talk about today, are analog Schlieren. And basically, whenever we talk about analog Schlieren, really what we are referring to is the use of optics, all right, lenses or mirrors, okay? Another way to do Schlieren is through digital Schlieren, which utilizes a speckled or textured background and some software to do the processing. And there are a lot of other methods, all right, which we won't talk about today. There's even some other Schlieren methods that we won't talk about today, but some include, for example, shadowgraphy, particle image velocimetry, just simple textured background imaging, and many more. All right, and I'm happy to chat about these at the very end if you have any questions. All right, so Schlieren imaging. The goal of most analog Schlieren experiments is to get the light, the refracted light to a detector. All right, and the way that scientists have done this is they utilize a point source of light. Okay, and this point source of light will emit isotropically. Okay, and if you put a lens at the focal length, at its focal length from this point source, this light will collimate. All right, and it'll basically, all the photons will move in a column. And then when they reach this condensing optic, they'll basically focus the light back down to a point. All right, and then you can project those photons onto a detector. All right, so now what you could do is you can place an event that induces a refractive index gradient. Okay, and for example, the candle, what it'll do is it will bend these collimated photons. Okay, and as these collimated photons come through, they'll be bent and they will no longer be collimated. All right, so what that does is it provides you the opportunity to have access to these non-collimated photons. So then you can cut them out of your image. All right, and this is the basic principle of Schlieren imaging. All right, and what that allows you to do is it gives you contrast to refractive index gradient. All right, so if you inspect this image here of this candle, all right, you see you have a beautiful representation of the refractive index gradient. All right, because we're getting all these refracted photons to the sensor. All right, and remember that the refractive index gradient depends on temperature, composition, and pressure, which is produced by this flame. All right, now you'll see that you have these darker areas in the image. All right, these darker areas of the image are photons that were blocked by what's called the knife edge. Okay, and you get this darker projection onto your sensor. Okay, then you also have photons that are bent around this focal point. Oh, I don't know what that was, but you basically have photons that are bent around the this focal point and make it to the sensor, and you'll see they're a little bit brighter here. Okay, so this is the essence of a Schlieren image. Okay, we also have a more common optical setup called a Z setup. All right, and these come in all shapes and sizes, the Schlieren setups. Okay, so in this case, instead of using a lens, you have a collimating mirror here, and this could be a parabolic mirror, it could be a spherical mirror. Okay, and what it does is it serves the same purpose. It collimates photons across this region of interest here, and then it puts the photons back into the sharp focal point, and then it'll project an image onto your sensor. Okay, so if we do the same thing, we put a candle in the path, you'll see that indeed you'll get that same type of effect. And the photons will refract, disturb your collimation, and then you'll get your Schlieren effect. Okay. So how do you know what to use, lenses or mirrors for your test? Okay, both work just fine, but your decision typically depends on the application of interest. Okay, and a lot of times it comes simply down to cross-section and your field of view that you care about. All right, so for lenses, usually they're available on the order of a few inches. All right, so that'll actually define your field of view. If you think back to the diagram, the collimated beam is roughly the cross-section of that optic, so that will define the FOV. All right, And then mirrors, all right, they're typically on the order of 1 to 2 feet. So obviously you can get them much smaller. People typically pick between spherical or parabolic, but the latter is more common. Parabolic mirrors are typically selected because they create a sharper focal point for the test. All right. So why can we only use, for example, optics that produce fields of view of 2 feet or less? All right. It comes down to commercial availability and costs. All right. You can find larger mirrors from other scientific equipment. Some people take advantage of telescopes, spectrometers, or different pieces from industrial equipment that have large mirrors in them, and they'll be repurposed for Schlieren. Okay. And we're going to talk a little bit more about how do you do Schlieren over much larger fields of view. All right. And that's going to take advantage of the digital methodology. Okay. So here's an example of a lens-based Schlieren system. This was done at Princeton University. Okay. And on the very left-hand side here, we had a fiber light. It was a photonic 5100 with a 300 micron aperture that created a point source of light. Okay. And then we had our collimation optics, a lens over here. It went through a wind tunnel here that was going above Mach 1. All right. And there was basically a subject in there that induced a shockwave event here. Okay. On the subject. All right. And then those photons came through the setup. They got collimated, they got condensed back down. There was a knife edge here, and then the image was projected onto a high-speed sensor. Okay. And the goal of the test was to visualize what the steady state looked like when the wind tunnel reached its max speed. Okay. And from this information, they can see the refractive index gradient of this event, and they were able to make some conclusions about some key lengths and angles that resulted from this cylindrical event being subjected to that high speed wind. All right. Another common test that was done, especially recently during COVID, was the ability to look at airflow when using masks. All right. This is a hot topic during COVID for obvious reasons. So you can use a mirror system to visualize the refractive index gradients coming from either the mouth or the nose. Okay. In some research endeavors, people want to know exactly how the air is flowing during flight. So for example, looking at drones, this is a small drone that's taking off. All right. And you can visualize all the flow fields that are occurring simply by putting this in a mirror-based system. Okay. So you can see some really interesting flow phenomena happening there. You can also look at shock waves during the explosions. So for example, if you put this in your mirror system, you can set off an explosion and you can see all the beautiful details from the shock wave that get produced. And you can even see some really interesting shock wave reflections off of the surface. You can see some interference, some destructive and constructive interference as this goes off. Really beautiful result. There's been a recent interest in welding studies. So on the left, you can see into the details of a CMT welding phenomenon. Okay, this was taken with a really fast 4 megapixel sensor, a phantom camera. And then on the left-hand side, this is the same test, but done in a Schlieren configuration. Okay, notice that with the Schlieren configuration, you can also see not only the detail of the weld, but you can also see the heat plumes that are flowing off of this event. Okay, and this was done with a Cavatar laser, and it was complements of Sidious imaging. Okay, you can even look at, for example, sound waves, ultrasonic waves as well. All right, so if you use a simple mirror system, you can produce sound waves, and you can use, for example, methods to reflect them and visualize them. All right. So imagine you ever have a test where you need to see exactly how the acoustic wave is changing or bouncing off different surfaces, or why certain sounds behave a certain way. You can use your Schlieren system to visualize that. Okay. You can look at the muzzle of weapons testing, okay? If you fire a weapon, you can see all the details of the pressure gradients inside and outside the muzzle as it fires, okay? Any sort of weapon testing that is focused on understanding the shockwave that gets produced or any of the acoustics that get produced, especially popular in the development of silencers. Schlieren is a really great tool for that. All right, you may have seen a lot of color Schlieren published in the literature and beyond. And the way you can do color is you have the same type of setup, okay? But instead of having, for example, a knife edge, you can put color filters at the focal point after the light passes through the event. And what you're basically doing is you're painting photons. You're basically painting their path. All right, you're not actually painting them, of course. You're filtering different wavelengths of light. And when this light refracts from the heat plume, all right, the photons that get pushed outside of the focal point and into the green region will be essentially filtered green. And then any photon that gets basically refracted to this other region, this red region here, all the photons will be filtered out except for the red ones, and you'll be able to see basically what photons were refracted in that region, okay? So by setting up this basic color filter setup, you'll be able to see that the refractive index gradient can be colored accordingly, all right? And yes, the directionality of the knife edge and the color filter gels are critically important to the final result of your test, all right? In general, it's recommended that if you have for example, a vertical type, like for example, this vertical cylindrical refractive index gradient, in general, to get the highest refractive index sensitivity, you're going to want to put your knife edge, for example, in the vertical direction, all right, to cut those photons, all right. We did an interesting test at MIT during their high-speed imaging course. We took this was for fun, we took an olive and we threw it through a bubble while it was in a Z configuration type setup. And you can see the refractive index gradient of that air that was inside. And it also makes for a very beautiful shot. This was done by my colleague, Phil Taylor, in Australia. Okay. Here, basically what happened is he shot a cork out of a bottle, and you can put this in a Z type color Schlieren setup, and you can get a beautiful refractive index gradient visualized. And you can basically see the different details in these mock diamonds. All right, and you can paint them essentially different colors to highlight the different behavior of the refraction. Here's a combustive event. For example, if you heat up a Bunsen burner, you can see all the beautiful details of that combustion using a color setup. Here, a match is lighting some lighter fluid on a angled table, for example. And the color Schlieren gives you a lot of beautiful detail of that event. Okay. All right, so what happens if you have a test with a relatively large field of view? Or maybe you can't afford expensive optics like lenses and mirrors, all right? Digital Schlieren is a method that you can do today in your home without any special optics or mirrors, okay? And there's two ways of doing that. One's called synthetic Schlieren, and the other one is called background-oriented Schlieren, okay? And if you look in the literature, sometimes these are mixed up, the terminology, but just know in this case, when I refer to synthetic Schlieren, I'm referring to just subtracting frames from each other. And background-oriented Schlieren is a more complicated software-based technique that allows you to see the refractive index changes, okay? So what does a typical background-oriented Schlieren setup look like, or a digital Schlieren setup in general look like? Basically, if it's a high-speed event, you'll have a high-speed camera, all right? You'll have a subject. This could be any event. It could be a person coughing. It could be, for example, something very destructive, an explosion or so on. And then in the background, you have a textured background. Here I have a speckled background, but this could be checkers. It could be a wide variety of different structures or textures here, okay? So there are some recommendations based on performing these tests. I'm not going to go into the details in this particular training or webinar, but just know that there's some optimization that can be done to the speckles. Here is where your refractive index gradient will exist, all right? And you want to make sure when you're doing digital Schlieren, you have damped vibrations, and you make sure you turn the fan off in the camera, all right? And you also want to make sure that you don't have any dangling cables like you see here. You want to make sure everything's fastened, because this technique is very sensitive to vibration. So to give you an idea of how this technique works, here I am in front of a speckled background. I'm just lighting a lighter, and maybe you can see it, maybe you can't, but as the heat plume basically comes off of that lighter, you'll see that the speckles or the texture behind the test are basically moving around, all right? And that's basically the digital Schlieren effect that we're looking for. If you just take this video and you subtract one frame from the next sequentially, you can do what's called fast frame differencing, and you can immediately highlight the details that are happening in this video from one frame to the next. And this technique is so sensitive that you can even see the heat coming off of my head in the video, all right? And very clearly, you can see how the heat plume evolves throughout the test. Now, fast frame differencing is good, but as you can see, you basically have a binary type result. And this doesn't have that much detail as compared to, for example, background-oriented Schlieren, which is different, all right? Here's a test done by Destin Sandlin of Smarter Every Day. He did the same type of test. Instead, he took a cannon and he fired it, okay? And he used the same technique where he subtracted one frame from the next, or he could have done every second frame, for example. And from the test, he was able to see that you get a beautiful shock wave that comes off of this cannon blast. And you can see really nicely the shock wave even going up a tree and traveling throughout this video very, very clearly, okay? You can even use Python. You can use Python to control a phantom camera. And if you basically look at a live image in using OpenCV and Python, you can do your synthetic Schlieren very nicely and easily just by using a few lines of code, okay? Now, what is background-oriented Schlieren? This is actually a more common methodology and a recommended technique because you get more detail in your digital Schlieren image, okay? So this is a result of background-oriented Schlieren, okay? This is a violent cough, all right? And notice that what's happening is the background-oriented Schlieren software is quantifying how much the background speckles distort, and then they apply a color that corresponds with the degree of that distortion. If you're familiar with something called digital image correlation, you'll notice that that same software can be used for this type of experiment, okay? Here's an example of a cough with a mask on, all right? And notice that you don't see the coughing flow that goes into the medium like in the previous video, okay? You may have seen this video from NASA that they posted, some beautiful jets flying through the atmosphere, and they can see these beautiful shock waves that come off their wings and the jet body, okay? How do they do that, okay? What they did is they used the same technique, except they very cleverly flew the airplanes over an area of the planet where it had this very unique speckled background, all right? And then they flew an aircraft above these jets, looking down on their flight. And then when they did some processing, they were able to use background-oriented Schlieren to get these beautiful results, all right? So just to show you what it looks like, if you can kind of make out with your eye that it's being distorted here, but with software, you can directly calculate the perturbation in the background and actually get a nice representation of the angles that come off the jet, okay? Now that's the conclusion of our webinar. I want to stress that we have hands-on technical trainings that we do on Schlieren imaging. This involves basically in-depth lecture, some more mathematics, and then hands-on training with high-speed cameras to do all sorts of different Schlieren setups, just to cement the concepts and get folks the ability to do Schlieren on their own, to use in their own research. And I will be open to any questions you may have.
Great, thank you so much, Kyle. We had quite a few questions come in, so I'm just going to go ahead and start them out here. The first one we had was with the lens after the knife. Is the camera the lens, and where should it be located for a prime 50mm lens, for example?
Yeah, it depends. Some people, for example, will not use a lens at all. They'll use a Schlieren setup as the lens. But as far as what lens you should use at what distance, that depends on your setup itself. So we'd have to look at your optical schematic and see what makes sense. And what you'd have to do is basically do, do some calculations. Some people will just put a piece of paper behind their Schlieren setup and see how the image projects onto it to see how it sizes. And if the image is too big for the sensor, then you would use a lens to resize it, and you could do some calculations to figure it out. So for the person who asked that, glad to help you out with that information, but we need to see what your setup looks like.
Great. The next one is, do you have any recommendations for selection of a light source?
Yes, we do. And it depends on what type of Schlieren you're doing. If you're doing Z Schlieren or you're doing background oriented Schlieren, you can reach out to us after this. I'll just go ahead and give a summary of what I recommend for the two most common types of high-speed setups. Is I always like to use the photonic 5100 fiber optic light. So basically it's an LED housed inside of basically a fixture, and you have a fiber that comes out like a neck, and you clamp the fiber, and you can put an aperture after it, and it's extremely luminous, and you can run really short exposure times with it. And that's what we recommend for doing Z type setups. At least that's what I'm used to recommending. You can go extremely fast with it. And then for background oriented Schlieren, if you want to basically do a test where you have, for example, a 6 foot by 6 foot background, for example, you can use either GS Vitek LED lights, or you can use IES 4438s. They're very, very bright lights, and you would use them to illuminate the background really nicely. And you want to be careful not to use LEDs that are not specific to high-speed imaging, because if they're not designed for high-speed imaging, they will flicker and they won't work good for you. All right. So the faster you go, you're going to need specialized lights to do that. But GS Vitek or IES are great lights to use.
Okay, and then carrying on with another question about light, does a smaller light source, is it better in terms of sensitivity and contrast?
Yes. Yeah, so I think the question, I guess another phrasing you could use for that question is, if you have a smaller point source, do you get better refractive index sensitivity? And the answer to that is yes. The caveat is that the smaller you make your light, right, the pinhole is the less light you get. So a lot of times it's a balance between getting great refractive index contrast and basically getting enough light, right? In theory, infinitely small is the best, but you don't have that luxury. So you have to play a little bit of a balancing game. So you make the aperture as small as you can, so you get a good image, and usually that's where you end. That's where you're stuck.
Great, thanks. Do you have any recommendations on where you can purchase color filters for color Schlieren?
Yes, there's a lot of nice optics companies. You can even get away with going on Amazon and looking up color filters, but you can go to Thor Labs or Edmund Optics. They'll have nice color gel filters to use for this, and they don't need to be really fancy. They can be pretty basic color filters. They'll work just fine.
Great, thanks. Are there any specific challenges for Schlieren imaging with liquids rather than gases?
Yeah, it's going to be different, right? So gases refract light less than liquids will. So you're going to have to be careful of that, because you could refract too much and not get good results. So Yeah, that's a little bit of a rabbit hole of a question, but let's say, for example, you have a fish tank and you're dropping hot water into cold water or something like that. There's a lot of ways to do that well, but maybe I won't go any further because it depends really on what your application is, all right, and how dramatic the refractive index change is. But each setup will have a different optimal recommendation. For example, whether it's, Z Schlieren or whether it's focused Schlieren and so on. So there's a lot of detail in there. And to get a good recommendation on how to set it up, we would need to see kind of your optical setup and what you're looking at, basically.
Great, thanks. Let's see, the next one was, are LEDs or lasers better? And then to follow on to that, if it is laser, then does pulse or continuous have an effect on what you're getting?
Yeah, absolutely. So people use both, right? And it depends on your budget sometimes. So for the most part, you can get away with using a very strong white LED fiber light, like I recommended. For most applications, you can do that. But there's some applications that will, let's say you need very short exposure times. All right, high-speed cameras, some of the best high-speed cameras on the planet can only go down to roughly 100 nanosecond exposure time, which may be too long. Whereas there's some lasers that exist for high-speed imaging. You can look at Cavatar lasers, or you can look at Oxford lasers, and they sell very powerful lasers, and they'll output anywhere between 500 and 1,000 watts of power, which is very impressive. And they allow you to pulse them to very short pulse widths. And that pulse width will be your effective exposure time. All right. So in reality, if you need the short exposure time, then pulse lasers are the way to go. But if you don't need that, you can run a continuous LED white light. That'll be fine. But again, it depends on your application for what is the best thing to use. Okay.
Great. In background oriented Schlieren, where do we focus the lens? In the background, the
Yes.
pattern, the subject?
Yeah, good question. The answer is all of it. So the reason why background oriented Schlieren is not that easy is because you need to make sure that your depth of field is fairly large, right? So your depth of field should extend from the subject to the background, because you want to, the speckles to be in focus, but you also want the subject to be in reasonable focus. And a lot of times it's very hard to do. And your ability to do that will be dependent on how bright your background is. So you want to pump as much light into the background as possible. I use a pair of those big LED lights to do that. For example, the IES 4438 is what I use for those. And then you want to take your lens aperture and you want to make it very small. Okay, when you make your aperture very small, it takes your depth of field and it stretches it out. All right, and that'll give you a good result. But yeah, that's it's not easy, but it can be done.
Great. So this one is could probably get into quite a bit of a rabbit hole for you too. But if you'd be happy to give resources to me, we can include it in the email that's going to follow up after this. Definitely would appreciate if you could point out additional detailed or specific resources and instructions for background oriented Schlieren.
Okay, yeah, and I think exactly that, Kenya. We have some nice documentation on how to set it up and some results from a little bit of background during COVID. Some people reach out to us and want us to do some research on masks. And we have a nice schematic that we drew out. In reality, your setup is going to be dependent on what you want to see, right? So if your field of view is like they use in the the JET study, that's going to be a little bit different than if you do a coughing study or if you do something on a smaller scale. You can either look at some of the documentation that Kenny's going to send out. That may help you. If it doesn't help you, you can reach out directly to us and we can go onto some nuanced recommendation for you.
Wonderful. Next one. Have you ever carried out quantitative evaluations of the Schlieren images? If yes, how did you do it?
All right. So the answer to that is, have I ever done it? have I been involved in cases where people have done it? Yes. The guy, if you're curious from the academic literature, you should look at the research done by Gary Settles and in Hargather or Hargather, however you want to pronounce it. They just recently, in the past, I would say 5 years, have been really pushing the envelope in terms of making Schlieren a quantitative measurement. Okay. Traditionally, Schlieren has only been qualitative, which means that you only can see the data and it just tells you where the plumes are going, which is great. But people want to know, what is the temperature? What is the pressure? What is the composition of my results? And the answer to that is, it's very hard, because refractive index is a function of temperature, pressure, and composition. So when you're seeing a refractive index gradient, it's hard to separate out those variables. All right. So if you look at some recent literature, and I'll be happy to share that with you if you want, you'll see that you can basically do this if you do it very carefully. And there's an article put out by Gary Settles that goes through the detail of how you would do that. And we'll share that
Yeah, well,
in the email.
we'll include that. There is a request for us to write their names, and I don't have that information on hand. So we'll include that in the follow-up email also, how to properly spell both of their names. So
Yep, no problem.
you can find that out. Next question. Can you comment on the applicability of background-oriented Schlieren for semi-transparent or transparent solid media?
I probably have to know a little bit more information. I mean, in reality, if you can get light through your subject, all right, then your subject's going to refract the light. All right. But you know, Schlieren is a photon starved high-speed imaging application. So so again, this is one of those things I'd have to know more detail about. I'm the type to just say, go ahead and test it, but you could do some back of the envelope calculation to see if it makes sense. But yeah, it's hard to know if that's possible without knowing more detail, unfortunately. Sorry.
Great. This would be the final question, unless somebody else drops one in while you're answering this one. Do you have experience with microscopic Schlieren images? What are the special challenges?
Great question. So there are companies that basically work specifically on this area. They do, for example, microscopic digital image correlation measurements. And I was debating whether to put this detail in here, but is it possible? Yes, you can certainly do it. But that is something that, you know, it's relatively new as far as what I've seen in literature. There's not much on it, but it's certainly possible. The challenge is that you're refracting photons over a very small scale, right? So you don't give them a lot of time to refract, but it is certainly possible to do it on a smaller scale. Absolutely.
Okay, we did have another question come in. It starts out with great talk. Thank you. I'm interested in how imaging is affected by having fluorescent molecules that might get excited in your fluid, or do we select filters to remove the excitation light?
Yeah, that's exactly right. I mean, if you have a test where you're exciting fluorescent markers or particles or whatever, yeah, you can certainly put a filter in there to get rid of the excitation. That'll work just fine. That's no problem.
Awesome. Okay, so that is all the questions that we have here. I do want to thank everyone who joined us live. It was a great turnout, really exciting. Glad to see that this is a good topic, and we had some phenomenal questions. So that's always wonderful to see. For those who are watching in the future, if you have any questions, please feel free to contact us via our website, and we will absolutely be happy to help you with these questions, anything you have, advisement on setup, etc. I will be sending out an email in the next day or so with a link to the video for everyone. Might take a little bit longer because I'm going to compile some of those extra data points that Kyle and I were discussing and make sure that I can get that out to everyone in the same single email. Other than that, I hope that you enjoyed the presentation And I hope that you all have a wonderful rest of your day and an absolutely fantastic weekend. Thank you so much for attending.
Bye, everybody.
Bye.